Good day, this is Professor Will, CBMD PhD, today Saturday, June 20th, 2020. It is 8:16:33 p.m. Eastern Standard Time. It is a continuation of my research on astronomy. So let's get started here. Today's self-quote: "Those who practice slowly learn quickly. So lay brick by brick as perfectly as you can, and eventually you'll have a wall." New light shed on intelligent life existing across the galaxy. Date June 15th, 2020. Source: University of Nottingham. Summary: is there anyone out there? This is an age-old question that researchers have now shed new light on with a study that calculates there could be more than 30 intelligent civilizations throughout our galaxy. This is an enormous advance over previous estimates which spanned from 0 to billions. One of the biggest, longest-standing questions in the history of human thought is whether there are other intelligent life forms within our universe. Obtaining good estimates of the number of possible extraterrestrial civilizations has, however, been very challenging. Using the assumption that intelligent life forms on other planets in a similar way as it does on Earth, researchers have obtained an estimate for the number of intelligent communicating civilizations within our own galaxy, the Milky Way. We calculate that there could be over 30 active communicating intelligent civilizations in our home galaxy. There should be at least a few dozen active civilizations in our galaxy under the assumption that it takes 5 billion years for intelligent life to form other planets, as on Earth. The idea is looking at evolution, but on a cosmic scale. We call this calculation the astrobiological Copernican limit. The classic method for estimating the number of intelligent civilizations relies on making guesses of values relating to life, whereby opinions about such matters vary quite substantially. Our new study simplifies these assumptions using new data, giving us a solid estimate of the number of civilizations in our galaxy. The two astrobiological Copernican limits are that intelligent life forms in less than 5 billion years, or after 5 billion years, similar to on Earth, where a communicating civilization formed after 4.5 billion years. In the strong criteria, whereby a metal content equal to that of the Sun is needed. The Sun is relatively speaking quite metal rich. We calculate that there should be around 36 active civilizations in our galaxy. Research shows that the number of civilizations depends strongly on how long they are actively sending out signals of their existence into space, such as radio transmission from satellites, television, etc. If other technological civilizations last as long as ours, which is currently 100 years old, then there will be about 36 ongoing intelligent technical civilizations throughout our galaxy. However, the average distance to these civilizations would be 17,000 light years away, making detection and communication very difficult with our present technology. It is also possible that we are the only civilization within our galaxy, unless the survival times of civilizations like our own are long. Our new research suggests that searches for extraterrestrial intelligent civilizations not only reveals the existence of how life forms, but also gives us clues for how long our own civilization will last. If we find that intelligent life is common, then this would reveal that our civilization could exist for much longer than a few hundred years. Alternatively, if we find that there are no active civilizations in our galaxy, it is a bad sign for our own long-term existence. By searching for extraterrestrial intelligent life, even if we find nothing, we are discovering our own future and fate. Is teleportation possible? Yes, in the quantum world, quantum teleportation is an important step in improving quantum computing. Date June 19, 2020. Source: University of Rochester. Summary: researchers are exploring new ways of creating quantum mechanical interactions between distant electrons. The research marks an important advance in quantum computing. "Beam me up" is one of the most famous catchphrases from the Star Trek series. It is the command issued when a character wishes to teleport from a remote location back to the Starship Enterprise. While human teleportation exists only in science fiction, teleportation is possible in the subatomic world of quantum mechanics, albeit not in the way typically depicted on TV. In the quantum world, teleportation involves the teleportation of information, rather than the teleportation of matter. Last year, scientists confirmed that information could be passed between photons on computer chips, even when the photons were not physically linked. Researchers recently discovered teleportation also may be possible between electrons. Research is an important step in improving quantum computing, which in turn has the potential to revolutionize technology, medicine, and science by providing faster and more efficient processors and sensors. Quantum teleportation is a demonstration of what Albert Einstein famously called spooky action at a distance, also known as quantum entanglement. In entanglement, one of the basic of concepts in quantum physics, the properties of one particle affects the properties of another, even when the particles are separated by a large distance. Quantum teleportation involves two distinct entangled particles. in which the state of the third particles instantly teleports its state to the two entangled particles. Quantum teleportation is an important means for transmitting information in quantum computing. While a typical computer consists of billions of transistors called bits, quantum computers encode information in quantum bits or qubits. A bit has a single binary value which can be either 0 or 1, but qubits can be either 0 and 1 at the same time. The ability for individual qubits to simultaneously occupy multiple states underlies the great potential power of quantum computers. Scientists have recently demonstrated quantum teleportation by using electromagnetic photons to create remotely entangled pairs of qubits. Qubits made from individual electrons, however, are also promising for transmitting information in semiconductors. Individual electrons are promising qubits because they interact very easily with each other, and individual electron qubits in semiconductors are also scalable. Reliably creating long-distance interactions between electrons is essential for quantum computing. Creating entangled pairs of electron qubits that span long distances, which is required for teleportation, has proved challenging. Though while photons naturally propagate over long distances, electrons usually are confined to one place. In order to demonstrate quantum teleportation using electrons, the researchers harnessed a recently developed technique based on the principles of Heisenberg exchange coupling. An individual electron is like a bar magnet with a north pole and south pole that can point either up or down. The direction of the pole, whether the north pole is pointing up or down, for instance, is known as the electron's magnetic moment or quantum spin state. Certain kinds of particles have the same magnetic moment. They cannot be in the same place at the same time. That is, two electrons in the same quantum state cannot sit on top of each other. If they did, their states would swap back and forth in time. Researchers use the technique to distribute entangled pairs of electrons and teleport their spin states. We provide evidence for entanglement swapping, in which we create entanglement in between two electrons even though the particles never interact. In quantum gate teleportation, a potentially useful technique for quantum computing using teleportation. Our work shows that this can be done even without photons. The results pave the way for future research on quantum teleportation involving spin states of all matter, not just photons, and provide more evidence for the surprisingly useful capabilities of individual electrons in qubit semiconductors. Researchers shed new light on solar flares. Date June 18, 2020. Source KU Leuven. Summary. Plasma astrophysicists have created the first self-consistent simulation of the physical processes that occur during a solar flare. The researchers use supercomputers and a new combination of physical models. Solar flares are explosives on the surface of the sun that release an enormous amount of energy, equivalent to a trillion little boy atomic bombs exploding at the same time. In extreme cases, solar flares can disable radio connections and power stations on Earth, but they are also at the basis of stunning space weather phenomena. The northern lights, for instance, are linked to the solar flare that disturbs the magnetic field of the sun to such an extent that a bubble of solar plasma can escape from the atmosphere of the sun. Thanks to satellites and solar telescopes, we already understand quite a lot about the physical processes that take place during a solar flare. For one thing, we know that solar flares convert energy from magnetic fields into heat, light and motion energy very efficiently. In science textbooks, these processes are commonly visualized as the standard 2D solar flare model. Details of this illustration, however, have never been confirmed. This is because creating a fully consistent simulation is a huge challenge. Given that both macroscopic effects, we are talking several tens of thousands of kilometers here, larger than Earth, and microscopic particle physics has to be taken into account. Researchers at KU Leuven have now been able to create such a simulation. The researchers used the computational power of Flemish supercomputers as well as a new combination of physical models, in which the microscopic effects of accelerated charged particles were taken into account in the macroscopic model. Our work also makes it possible to calculate the energy conversion efficiency of a solar flare. We can calculate this efficiency by combining the strength of the sun's magnetic field at the feet of the flare with the speed at which those feet move. If we can complete our observations in time, that is because everything happens within a time span of tens of seconds to a few minutes. We converted the results of the numerical simulation into virtual observations of a solar flare, whereby we imitated telescopes in all relevant wavelengths. This allowed us to upgrade the standard solar flare model from a textbook illustration to an actual model. Good day, this is Professor Will, CVMD PhD on infectious disease, molecular microbiology, and astrophysics. Well, hope you enjoyed listening. Until next time, have a great day.